Hello. Thank you for watching this video for our paper, Mask Balancing, Perception-Driven Dynamic Visibility Enhancement for Occlusion-Capable Optical See-Through Head-Mounted Displays. I am Zhang from Shanghai Jiao Tong University. This work is a collaboration with Nara Institute of Science and Technology, Graz University of Technology, and Zhejiang University of Science and Technology. Occlusion-Capable Optical See-Through Head-Mounted Display, here we call it OC-OSTHMD in abbreviation, is proven to make AR display more vivid by enabling mutual occlusion between the virtual objects and the real scene, as shown in the left. However, the attractive feature relies on letting real light pass through the device's optical system, which severely dims the real scene at the same time, hindering practical application. For example, the right table lists the optical surface that the real scene light propagates in our OC-OSTHMD prototype at IEEE VR 2023. Considering the optical equivalent structure, there is one polarizer, one spatial light modulator, 7 polarizing beam splitters, and 6 quarter-wave plates, each of which contributes to optical power loss, resulting in a see-through efficiency below 10%. In comparison, the see-through efficiency is around 40% in HoloLens 2. To tackle this issue, we propose a perception-driven solution called mask balancing. The core idea is blending the processed real image with the bypassed real light. The bypassed light is orthogonally polarized to the processed part, preserving 50% of the optical power and containing the real image without occlusion processing, whereas it is fully blocked in the traditional design of OC-OSTHMDs. As a result, blending dramatically increases the brightness of the perceived real image, while decreasing the visibility of the virtual image. Hence, we leverage the blending in a perception-driven approach. The dynamic blending maintains good visibility of both the real scene and the virtual images simultaneously, as shown in the right figure. Here, we provide an overview of the proposed method. The OC-OSTHMD integrates an eye camera and a scene camera, and the balancing linear polarizer can be rotated electrically. With the configuration, both the virtual image and the real scene can be captured in real time. The image contrast is then computed. The virtual image contrast is compared with visible thresholds determined in user studies. The scene image contrast is compared to the eye contrast threshold, evaluated by traditional psychophysical functions and the user's pupil diameter. Finally, the cross angle of the balancing LP varies to provide optimal transmittance for both the virtual image and the real scene. The left figure shows a typical structure of OC-OSTHMDs, in which the core component is the polarizing beam splitter. The PBS separates the incoming natural light into s-polarized and p-polarized components. The s-polarized light enters the optical system of OC-OSTHMD and is processed to support mutual occlusion, while the p-polarized light bypasses the optical system after passing through the PBS. As both of them provide real scene vision, the balancing LP can be rotated to modulate the blending ratio, thereby increasing the real scene brightness to 50% at most. Of course, the transmittance of virtual image light is modulated simultaneously. The equation on the right describes the variation in transmittance as the cross-angle phi changes, according to Malice's law, where THMD and T-display are the intrinsic transmittances of the processed real scene and the virtual images produced by the device. The dominant advantage of this hardware design is the excellent versatility. The structure can be integrated into OC-OSTHMDs, as a PBS already exists in most of them, and a balancing LP can be easily added with low cost. Because brightness modulation of the real scene and the virtual image is coupled, we evaluate their visible thresholds to drive the balancing LP. We first conduct user studies to measure the threshold for the texture of virtual images, using Weber contrast metrics. The experimental setup is shown on the left. Virtual images are displayed by the OC-OSTHMD, and the real background is displayed by a projector. We use black text in 3 sizes to simulate texture with various spatial frequencies. The larger the text, the lower the spatial frequency is. All texts include a random number and are displayed on basic geometries. The real background is cropped from the color checker and has 4 luminance levels. The cross angle of the balancing LP is initially set as 5 degrees, making the outlines of virtual objects barely visible. Then, participants are guided to adjust the rotation of the balancing LP by the keyboard until the text string is just noticeable. After they find the just noticeable angle, participants are asked to click the recording button on the keyboard and report the number in the text for confirmation. Each condition in the experiment is repeated 3 times, leading to 36 trials in total. Another user study is designed to evaluate the visible threshold of the lighting effect on virtual objects. The same hardware setup is used in the user study. During the experiment, 6 pairs of virtual objects are displayed on the real background. Each pair consists of 2 identical meshes, while only one is rendered with lighting. The image pairs are displayed with a cross angle of 90 degrees, making their differences fully noticeable. Then, participants are asked to rotate the balancing LP until the paired images appear identical. We categorize virtual objects into high, medium, and low frequency groups based on their power spectral distributions, yielding 3 conditions. Meanwhile, the real background is with 4 luminance levels. As a result, we have 24 trails in total. The experiment results of the 2 user studies are shown in the 2 figures. A significant difference in the visible threshold is found between high and medium to low spatial frequencies, while image spatial frequency is not significant for lighting recognition. As a consequence, we set the upper limits of texture and lighting recognition as the visible thresholds for virtual images in the high and medium to low spatial frequency, respectively. To obtain the visible threshold of the real scene, we decompose the captured scene by the scene camera into bandpass images, as shown in the left figure. The spatial frequency of bandpass images is increased by an octave, from 0.6 cycles per degree to 37.4 cycles per degree, as shown in the bottom right figure. Then, we compute the RMS contrast of a bandpass image and test its visibility to the user by using the function here. CR is the bandpass RMS contrast, and SC is the eye contrast sensitivity to the bandpass, which can be computed by using Barton's contrast sensitivity function. The bandpass strategy benefits the method by focusing on improving the visibility of the crucial image feature in a complex real scene, enabling a task-oriented experience. The system dynamically triggers the balancing LP when either visibility test fails, based on the visible thresholds of the real and virtual images. We conduct the final user study to compare users' preferences for the same animated AR scene displayed on OC-OSTHMD with the mask balancing method, the typical OC-OSTHMD method, and the typical OSTHMD method. The animation is composed of 4 subscenes, whose illuminance ranges from 8 to 414 candela per square meter in sequence. 24 participants joined the user study and completed a paired comparison of the 3 display strategies. The video presents the perceived scene by using the 3 display strategies in the experiment. Participants were asked to choose the preferred strategy, depending on their overall experience and the subscene's experience, in each paired comparison. The curves illustrate the captured pupil diameter and the optimal cross angle of the balancing LP by the visibility test. The experimental results are shown in the figure. Overall, 50% of participants chose OC-OSTHMD with mask balancing as their preference, with 36% and 14% preferring typical OC-OSTHMD and OSTHMD, respectively. In detail, typical OC-OSTHMD performs worst in the indoor light-off subscene due to poor visibility of the real scene, whereas the optimization by mask balancing achieves a comparable score to typical OSTHMD. As the real scene becomes brighter, the preference for typical OC-OSTHMD increases, demonstrating the appealing image quality by adding mutual occlusion. On the contrary, typical OSTHMD is less selected due to its ghost-like virtual image. In comparison, our solution achieves the highest score, since it balances the visibility of both real and virtual images. In summary, our main contribution is a perception-driven approach that addresses the dimming vision issue in OC-OSTHMDs, a crucial step toward practical applications of the device. In addition, we evaluated the visible thresholds of the virtual images in AR displays. Whilst the visibility of OC-OSTHMDs is improved considerably, our method degrades the occlusion quality due to the blending with the bypass real image. The next step will be to evaluate and integrate the perceptual threshold for mutual occlusion into the mask balancing method. Thank you for watching.